Our first question today focuses on emergent abilities. At what scale do emergent abilities typically appear in language models? Your options are A. Millions of parameters, B. Billions of parameters, C. Thousands of parameters, D. They appear at all scales. The correct answer is B. Billions of parameters. We chose this answer because emergent abilities are breakthrough capabilities that only appear when AI models reach massive scale with billions of interconnected components working together. Here's the complete definition. Emergent abilities in large language models are capabilities that suddenly appear when models reach massive scale with billions of parameters. These are abilities that weren't explicitly trained for but emerge naturally from the complex interactions within the neural network. In simple terms, unexpected superpowers arise from massive scale. The layman explanation tells us that emergent abilities are like a jazz orchestra where individual musicians, when they reach critical mass and work together, create beautiful complex music that no single musician could produce alone. These abilities emerge spontaneously from the collective intelligence of billions of interconnected components. Simply put, teamwork creates magic at massive scale. Our real-time example shows that GPT-3 with 175 billion parameters can suddenly perform arithmetic, translate languages, and write code, abilities it was never specifically trained for. It's like teaching someone to read, and they spontaneously learn to write poetry. Smaller models with 1 billion parameters cannot do this, but at billions scale, magic happens. Bottom line, billions unlock hidden talents. The memory tip says billions bring breakthroughs. Remember that emergent abilities appear at the billions of parameters scale, not millions or thousands. Key takeaway: billions equals breakthroughs. Our next question explores chain of thought reasoning. What does chain of thought prompting encourage models to do? A. Generate longer responses. B. Show intermediate reasoning steps. C. Use more complex vocabulary. D. Increase output diversity. The answer is B. Show intermediate reasoning steps. This is correct because chain of thought specifically focuses on making the AI's thinking process visible and transparent, breaking down complex problems into logical step-by-step progressions. The definition states, chain of thought reasoning is a prompting technique that encourages AI models to break down complex problems into step-by-step reasoning processes, making their thinking visible and more accurate by showing the logical progression from question to answer. In essence, making AI thinking transparent improves accuracy. The layman explanation compares this to asking someone a math problem. Instead of just blurting out the answer, chain of thought is like asking them to show their work, explaining each step of their thinking process. This makes AI more accurate and helps us understand how it reaches conclusions, like having a transparent window into the AI's mind. Simply, showing work improves performance and understanding. Our example demonstrates the difference. Without chain of thought, asking what's 25% of 80 gets just the answer 20. With chain of thought, the AI explains, let me solve 25% of 80 step by step. First, 25% equals 25 divided by 100 equals 0.25, then 0.25 times 80 equals 20, therefore 25% of 80 is 20. Accuracy jumps from 60% to 85% with this method. Result: step-by-step thinking boosts accuracy by 25%. The memory tip suggests thinking of a chain where each link is a reasoning step, connecting the question to the final answer. Remember, chain equals connected reasoning steps. Our next question covers Retrieval-Augmented Generation. What does RAG combine? A. Multiple language models. B. Parametric knowledge and retrieved information. C. Different training objectives. D. Various tokenization methods. The correct answer is B. Parametric knowledge and retrieved information. This is right because RAG specifically combines what the AI already knows from training with fresh information it can retrieve from external sources in real time. Here's the complete definition. Retrieval-Augmented Generation, or RAG, is a technique that combines an AI model's built-in knowledge, called parametric knowledge, with real-time information retrieval from external databases or documents, creating more accurate and up-to-date responses. In short, combining AI memory with live information lookup. The layman explanation describes RAG as having a brilliant scholar, the AI model, who also has instant access to the world's largest library, which represents external databases. Instead of relying only on what they memorize during training, they can quickly look up current information and combine it with their existing knowledge to give you the most accurate, up-to-date answer possible. Think of it as AI brain plus instant library access. Our real-time example shows you asking about Tesla stock price today. A regular AI might say, I don't know current prices, limited by training data, but RAG retrieves real-time stock data at $180.25 and combines it with the AI's knowledge about Tesla to say Tesla stock is currently at $180.25, up 2.3% today, likely due to positive earnings from their energy storage division. The result: current data plus AI analysis. The memory tip suggests thinking RAG equals brain plus Google. Remember that RAG combines the AI's brain, which is parametric knowledge, with Google-like search, which is retrieved information. Key point: RAG means smart memory plus live search. Our next question examines multimodal models. How do multimodal LLMs typically process images? A. Converting to text descriptions. B. Using vision encoders to create embeddings. C. Pixel-by-pixel analysis. D. Separate processing pipelines. The answer is B. Using vision encoders to create embeddings. This is correct because multimodal models use specialized vision encoders that convert visual information into mathematical representations called embeddings that the language model can understand and work with. The full definition explains: multimodal language models are AI systems that can understand and process multiple types of input simultaneously, typically text and images, by converting visual information into mathematical representations called embeddings that the language model can understand and integrate with text processing. Simply stated, converting different inputs into common mathematical language. The layman explanation describes multimodal models as universal translators that convert different languages of information into one common mathematical language. Images get translated into numerical embeddings like DNA codes that the text processing brain can understand, allowing seamless communication between visual and textual understanding. In other words, universal translation enables cross-modal communication. Our example shows you presenting GPT for VA photo of a sunset with text asking to describe this image. The vision encoder converts the sunset pixels into mathematical embeddings like 0.234, 0.891, 0.156, which the language model interprets as golden sky, orange clouds, horizon line, and responds this is a beautiful sunset with warm orange and golden hues painting the sky above the horizon. The process: pixels become math, math becomes understanding. The memory tip says vision encoder equals image translator. Remember that vision encoders translate images into the mathematical language that LLMs understand. Key concept: vision encoders are image-to-math translators. Our final question focuses on mixture of experts. What is the main advantage of mixture of experts, or MO, models? A. Simpler architecture. B. Scaling model capacity without proportional compute increase. C. Faster training. D. Better interpretability. The correct answer is B. Scaling model capacity without proportional compute increase. This is right because MO allows you to have massive model capability while only using a fraction of the computational resources through intelligent expert selection. The complete definition states, mixture of experts, or MO, architecture is a neural network design that contains multiple specialized expert networks, but only activates the most relevant experts for each input, allowing massive model capacity while keeping computational costs manageable through intelligent expert routing. In essence, massive capability with efficient resource usage. The layman explanation compares this to a hospital with 100 specialist doctors, but each patient only sees the 2 or 3 most relevant specialists. MO works similarly. It has many expert networks like specialists, but intelligently routes each input to only the most relevant experts, getting the benefit of massive expertise without the cost of consulting everyone. Simply put, Smart routing maximizes expertise while minimizing costs. Our example demonstrates Google's Switch transformer has 1.6 trillion parameters, but only uses 2 billion per input. When you ask about cooking, it routes to culinary experts. Ask about coding, it routes to programming experts. It's like having 1,000 specialists but only paying for 2 consultations, delivering massive capability at a fraction of the cost. The outcome: trillion parameter power with billion parameter efficiency. The memory tip suggests Mo equals more for less. Remember that mixture of experts gives you more capacity for less computational cost through smart routing. Final thought: Mo delivers maximum intelligence with minimum resources.